You wake up and the sky is the wrong color, not blue, not gray with rain. A deep, bruised orange that stretches from one horizon to the other, the kind of orange you only see in photographs of disasters that happened somewhere else to someone else. Except this time it's everywhere, every continent. Every ocean, because somewhere at the exact same moment, every single volcano on Earth just woke up with you. There are roughly 1,500 potentially active volcanoes scattered across the planet right now. Most of them sit quietly for centuries, sometimes for thousands of years, doing nothing more dramatic than venting a little steam. But imagine just for a moment that the geological clock resets all at once. Every dormant giant, every smoking cone, every underwater vent along the mid-ocean ridges, erupting in the same instant. It's not something geology has ever actually done. But asking why it hasn't and what would happen if it somehow did tells you something remarkable about how fragile the balance actually is. Let's start with what you'd see first, because the visible destruction is almost the least of it. Coastal cities near the Pacific Ring of Fire, home to roughly 75% of the world's active volcanoes, would face lava flows, pyroclastic surges, and ashfall within minutes. Tokyo, Jakarta, Manila. Mexico City, Seattle, sitting in the shadow of Mount Rainier. These aren't hypothetical dangers, they're cities that already live with active volcanoes on their doorstep, built on the assumption that catastrophe stays rare. Now multiply that single doorstep by 1,500, all opening at the same time. What happens to a planet where evacuation isn't an option because there's nowhere left that isn't also on fire? Here's where the science gets genuinely strange, because the immediate blast radius isn't actually the biggest threat. It's what comes after, high up in the atmosphere, invisible for weeks before it changes everything. The volcanologist Clive Oppenheimer has spent much of his career studying the 1815 eruption of Mount Tambora in Indonesia, the largest volcanic eruption in recorded human history. Tambora alone, a single mountain, threw enough sulfur dioxide into the stratosphere to trigger what became known as the year without a summer. Crops failed across Europe and North America. Snow fell in June in New England. Famine and disease followed in Tambora's wake for years, all from one eruption on one island. Now picture 1,500 Tamboras going off together. Does the atmosphere even have a word for what that would do to it? It does actually, and it's a chillingly familiar one, the climate scientist Alan Robock, who has spent decades modeling both nuclear winter and volcanic winter scenarios, found that large-scale eruptions inject so much sulfate aerosol into the stratosphere that sunlight itself gets scattered back into space before it ever reaches the ground. Robock's models show that even a handful of large simultaneous eruptions could drop global temperatures by several degrees for years at a time. A worldwide eruption event wouldn't just darken the sky for a few dramatic sunsets. It would dim the sun itself, gradually, relentlessly, for seasons on end. What does a planet look like when the growing season simply stops arriving? Think about what that means for something as basic as a wheat field. Photosynthesis needs sunlight, and sunlight is precisely what a global sulfate veil is built to block. Within a single growing season, staple crops across entire continents could fail simultaneously, not because of drought or flooding in any one place, but because the light itself has dimmed everywhere at once. Grain reserves that normally cushion a bad harvest in one region assume that other regions are having a good one. What happens to a global food system built entirely on that assumption the moment every region has a bad harvest in the exact same year? There's a deeper, older story buried inside this question, and it comes from Earth's own past. Roughly 74,000 years ago, the Toba supervolcano in Sumatra erupted with a force many times larger than Tambora, ejecting an estimated 2,800 cubic kilometers of material into the atmosphere. Some researchers have proposed what's known as the Toba catastrophe theory, the idea that the resulting volcanic winter pushed early human populations to the edge of extinction, shrinking our species down to a genetic bottleneck of just a few thousand individuals. The theory remains debated among geneticists and archaeologists, and newer evidence complicates the story considerably. But even as a contested hypothesis, it hints at something worth sitting with. Humanity may have already survived something close to this scenario once, clinging on by a thread nobody at the time could have seen. So could we survive it again? The geologist and hazard researcher Bill McGuire has spent years studying how geological events interact with a warming, densely populated modern world, and one of his central warnings is that we've built global civilization with almost no redundancy for a shock this size. Supply chains span oceans. Just-in-time manufacturing means most cities hold only days of food reserves at any given moment. Modern agriculture depends on predictable seasons in a way subsistence farming never fully did. McGuire's research suggests that a truly global catastrophe wouldn't need to kill people directly through lava or ash. It would simply need to interrupt the enormously complicated, enormously fragile systems that already keep 8 billion people fed, warm, and alive. Is that more frightening than the eruptions themselves, or less? Before the ocean, though, there's one more category worth pausing on, because not all volcanoes are created equal. Somewhere beneath Yellowstone National Park sits a supervolcano capable, on its own, of an eruption thousands of times larger than anything in modern memory. Similar giants sleep beneath Lake Toba itself, beneath the Campi Flegrei caldera near Naples, and beneath a handful of other calderas scattered across the globe. In any realistic geological timeline, these supervolcanoes erupt independently, separated by tens of thousands of years, each one a singular catastrophe the planet slowly absorbs before the next arrives. In this thought experiment, though, they'd all be going off at once, alongside every smaller volcano on the list. It's the difference between a single earthquake and every fault line on Earth slipping in the same second. Does scale like that even register as one disaster, or does it stop being a single event at all and become something closer to a new geological era beginning in real time? Now zoom back out to the ocean, because more than 80% of all volcanic activity on Earth actually happens underwater, along the mid-ocean ridges where tectonic plates pull apart. A simultaneous global eruption wouldn't just choke the sky. It would flood the oceans with volcanic gases, spiking carbon dioxide levels and acidifying seawater far faster than anything currently driving modern ocean acidification. Coral reefs, already stressed by rising temperatures, could collapse within months rather than decades. Entire marine food chains, from plankton up through the largest fish, would face a chemical shock they've never encountered on this timescale before. Does the ocean recover from something like that in years, or in geological ages measured in tens of thousands of them? Here's a strange twist buried inside the chaos, though, something almost nobody expects. Volcanic ash, once it settles, is extraordinarily rich in minerals. Some of the most fertile farmland on Earth today sits directly on top of ancient volcanic soil in places like Java, the Pacific Northwest, and the slopes of Mount Etna in Sicily. In the decades after a hypothetical simultaneous eruption, once the ash finally settled and the sulfate veil finally cleared, an enormous amount of newly enriched soil would exist across the planet. Would the generation born into the recovery inherit some of the most fertile land in human history, purchased at the unimaginable cost of the generation that lived through the collapse? That question gets at something important about disasters at this scale. They're rarely just destruction followed by nothing. They're destruction followed by an entirely different world, one that operates under different rules than the one that came before it. Governments would almost certainly fall or fundamentally restructure, unable to manage a crisis with no historical precedent to guide the response. Populations would shift dramatically toward whatever regions retained functioning agriculture and clean water, probably concentrated near the equator, where sunlight, however dimmed, would remain strongest. Entire industries built around predictable climate, from insurance to international shipping, would need to be rebuilt from something closer to first principles. And yet humanity has a strange, stubborn track record of getting through exactly this kind of thing before, even if the Toba story remains scientifically uncertain. After Tambora's eruption in 1815, communities that seemed doomed to famine found ways, however brutal and unequal, to adapt within a handful of years. Crops were replaced, migration patterns shifted, and eventually the sulfate veil cleared and the sun came back in full. A truly global, simultaneous eruption would be vastly worse than Tambora, by orders of magnitude nobody has ever had to calculate for real. But the underlying pattern, darkness, adaptation, eventual recovery, is one this planet and this species have walked through before, just never at anything close to this scale. There's also a quieter kind of recovery worth imagining, one that has nothing to do with soil or sunlight. Disasters this large tend to compress decades of technological urgency into just a handful of years. Underground and vertical farming, largely a niche experiment today, would almost certainly become a survival necessity within the first 18 months, since it doesn't depend on direct sunlight the way traditional agriculture does. Nations with existing greenhouse infrastructure, geothermal heating, or advanced desalination could find themselves holding an entirely new kind of geopolitical leverage. Not oil, not military strength, but the simple ability to grow food indoors at scale. Would the countries best equipped to survive a volcanic winter even be the ones considered wealthiest today? Or would resilience turn out to belong to places nobody currently thinks to rank at the top of anything? Consider, too, what happens to information itself in the first chaotic days. Satellites, the invisible backbone behind weather forecasting, GPS navigation, and global communication, would face an atmosphere thick with ash and static electricity capable of disrupting signals across entire regions. Emergency broadcasts would compete with silence in places used to instant updates. For a species that has grown almost entirely dependent on knowing what's happening everywhere else in real time, the sudden return of genuine, old-fashioned uncertainty might be nearly as disorienting as the eruptions themselves. Would people panic faster in a blackout of information? Or would the shared confusion actually pull neighborhoods and cities together in ways today's constant connectivity rarely allows? Maybe that's the most unsettling part of the entire thought experiment. Not the lava, not even the darkened sky. It's the realization that the systems keeping you fed, warm, and connected to the rest of the world are built on an assumption so basic nobody questions it, that the ground beneath your feet and every other person's feet on every continent stays quiet at the same time. It never has, at least not that we know of. It probably never will, but the fact that it hasn't isn't a law of physics. It's a streak of geological luck stretching back further than recorded history that every civilization on Earth has been quietly, unknowingly betting on. You wake up and the sky is the wrong color, except this time you understand exactly why and exactly how close that color has always been to becoming real.